In this study, we've developed a parallel framework for performing dimensionality reduction on streaming data. Our approach has led to the creation of a technique called SDR, which enables fast, reliable, and stable dimensionality reduction for streaming data. DR techniques are widely used for visualizing high-dimensional data. It employs a metaphor: proximity is roughly equivalent to similarity. Thus, the data similarity is retained by the distance between their embeddings, helping users to analyze data patterns like clustering and anomalies. However, the effective application of dimensionality reduction for analyzing streaming data remains somewhat uncertain. Streaming data introduces three distinctive characteristics when compared to static data. Firstly, streaming data is continuously generated at a high rate. Secondly, the patterns within streaming data evolve over time. Thirdly, visualizing streaming data demands the constant updating of views to accommodate these data changes. We aim to develop an innovative streaming dimensionality reduction technique to address these gaps, and we've identified three key requirements for this technique. The first requirement is high speed. It needs to process data at a pace that matches the rate at which data arrives. The second requirement is adaptability to changes in data patterns, which ensures the reliability of the embedding results. The third requirement is temporal stability. Even when data patterns change, the DR method should maintain the stability of the embedding results, assisting analysts in retaining a consistent mental map and reducing cognitive load. However, meeting these requirements is not a straightforward task. Regarding speed, the streaming DR process typically involves three modules: new data embedding, embedding function updating, and embedding updating. Each of these modules demands substantial computation. The technical decisions made in implementing these modules and their coordination play a pivotal role in determining the method's overall performance. Regarding the adaptation to changes in data patterns, non-parametric methods entail recalculating all data embeddings, which can be quite time-consuming. Some parametric methods suggest incrementally updating the embedding function based on new data, but this approach often results in lower embedding quality. The challenge of striking the balance between speed and the quality of adapting to changes in data patterns remains an unresolved issue. When it comes to preserving the stability of embedding results, it involves a trade-off with maintaining reliability of the embeddings. This is because maintaining reliable embeddings necessitates continuous updates to reflect the latest data patterns. Effectively striking the right balance between the reliability and stability of embedding results is also a non-trivial challenge. To tackle the aforementioned challenges, we introduce a streaming dimensionality reduction approach known as SDR. Firstly, we present a parallel streaming DR framework and incorporate efficient calculation strategies into each specific module to enhance processing speed. Secondly, we introduce an incremental learning method designed for parametric DR techniques to accommodate changes in data patterns. Additionally, we incorporate a visual feature-based adaptive stability constraint into the incremental updating process, ensuring the stability of the embedding results. Here is an overview of the parallel framework and the pipeline for SDR. The pipeline consists of three modules: the new data embedding module, the embedding function updating module, and the embedding updating module, all running in parallel. New data will be fed into these three modules simultaneously. The new data embedding module calculates embeddings for the incoming data, while the embedding updating module updates the existing embedding results. The embedding function update module initially stores data and updates the embedding function when the buffer reaches its capacity. This updated embedding function is subsequently employed for computing embeddings for future incoming data. Let's first take a look at the design of the parallel framework. The key of the parallel framework is to resolve the dependence among the three modules. Initially, we opt for a parametric DR approach to address the interdependence between the new data embedding module and the embedding function updating module. In contrast to traditional DR methods that necessitate the updating of their implicit embedding function before handling new data, parametric methods have the advantage of directly embedding new data using an explicit function. Secondly, we address the dependency of the embedding updating module on the embedding function updating module through a hybrid embedding updating strategy. In this approach, the embedding updating module only invokes the updated embedding function when it detects global changes. Otherwise, it exclusively conducts local updates using numerical optimization methods. Thirdly, to address the dependency between the embedding updating module and the embedding results of newly arriving data, we have these two modules operate in parallel, but with an asynchronous approach. To be more precise, the embedding updating runs one step behind the new data embedding. The efficiency gained from this approach comes at a slight cost to embedding quality due to the minor time lag. At this stage, all dependencies among the three modules have been resolved, enabling them to work together efficiently in parallel. Next, let's have a brief overview of our specific design for each module. For the new data embedding module, we opted for CDR, a parametric nonlinear DR method. CDR utilizes an embedding function rooted in neural networks to explicitly compute data embeddings. By leveraging a contrastive learning approach and redefining the gradient of the contrastive loss, CDR can produce reliable embedding results characterized by distinct visual cluster separation. Within the embedding function updating module, our primary concerns are updating speed, quality, and stability. To address these aspects, we introduced an adaptive incremental learning method for updating CDR's embedding function. This method aims to strike a balance between the embedding quality and stability over time. It comprises a similarity-based quality constraint, a perception-based stability constraint, and an adaptive updating strategy. To ensure the embedding quality of both existing and new data, our similarity-based quality constraint encompasses a learning loss and a preservation loss. The learning loss ensures the embedding quality of new data by learning the similarity within the new data and between the new and existing data. Meanwhile, the preservation loss safeguards the embedding quality of existing data by constraining changes in the similarity among the existing data. Stable embedding results over time can assist analysts in gaining a deeper understanding of the context and relevance of data changes. However, the inherent randomness of algorithms during an updating process has the potential to disrupt the stability of the embedding results. Hence, we conduct an analysis of the typical visual clustering features, which are based on user perception in DR tasks. We then incorporate a temporal stability constraint to preserve these visual features, with objective of retaining the relative positions, distances, shapes, and sizes of visual clusters. As previously mentioned, preserving embedding quality and stability involves a trade-off. When updating the embedding function, it's crucial to strike a balance between these factors in response to changes in data patterns. To achieve this, we introduce the stability constraint weight, enabling data embeddings to be updated when data patterns change, while keeping other data embeddings stable. In this figure, it's evident that embedding results can effectively uphold both high quality and stability when employing the adaptive incremental updating strategy that integrates stability constraints. During the embedding updating process, existing methods typically entail recomputing embeddings for all data, which can lead to significant computational overhead. However, in streaming data, pattern changes mostly occur locally, making the complete recomputation of embeddings for all data often unnecessary. As a solution, we introduce a hybrid embedding updating strategy built on a divide and conquer principle. Initially, we employ a KNN-based detection algorithm to discern changes in local structures or global patterns. In cases of local structure changes, we update local embeddings using a Causey-Newton optimization method. When global pattern changes are detected, we use the updated embedding function to recalculate embeddings for all data. Subsequently, we conducted extensive experiments to assess whether SDR meets all three of these requirements: high speed, adaptability to changes in data patterns, and temporal stability. We selected 4 streaming DR techniques, namely streaming PCA, X-streaming, S-isomap++, and instance-based neighbor embedding. These experiments were conducted on 5 real-world datasets. To begin, we partitioned each dataset into 2 distinct sets, one for pre-existing data used for model initialization, and another for streaming data employed in testing. Recognizing the diversity in streaming data change patterns and their varying impacts on algorithms, we simulated 3 different situations when dividing each dataset. Mode 1. All new data originates from existing categories. Mode 2. All new data belongs to entirely new categories. Mode 3. New data comprises a mix of both existing and new categories. Regarding runtime performance, SDR demonstrated the most impressive overall results. Streaming PCA exhibited higher throughput on the lower dimensional datasets. However, its performance noticeably declined as the dimensionality increased. In contrast, SDR consistently performed well across various data dimensions and different streaming data change patterns. In terms of embedding quality, it's evident that SDR excels significantly in preserving local structures compared to other methods. However, when it comes to preserving global distance relations, SDR falls slightly behind X-streaming. This distinction can be attributed primarily to the distinct optimization objectives pursued by SDR and X-streaming. Furthermore, SDR superiority in embedding quality remains consistent across various streaming data change patterns. In the realm of embedding stability, SDR consistently exhibits significantly lower levels of embedding changes compared to streaming PCA and X-streaming. As depicted in Figure 2, it's evident that SDR's embedding results undergo less frequent and less substantial fluctuations than those of streaming PCA and X-streaming. Additionally, we conducted ablation experiments to validate the effectiveness of our proposed methods. The ablation experiments for the parallel framework confirm its significant contribution to performance improvement. Regarding the loss terms in the incremental updating process, our experimental results demonstrate that the quality constraint effectively ensures the quality of the embedding results. And the learning loss and preservation loss play distinct roles in maintaining the embedding quality of existing data and new data respectively. Furthermore, the results indicate that the stability constraint effectively ensures the stability of embedding results. Figure 3 reveals that each subconstraint within the stability constraint upholds distinct types of visual features. In summary, our work introduces a streaming dimensionality reduction technique. This includes a parallel framework aimed at enhancing the efficiency of the streaming DR pipeline, an incremental learning method to accommodate changes in data patterns, and a visual feature-based adaptive stability constraint to maintain temporally stable embedding results. It's worth highlighting that the parallel framework and adaptive incremental learning method can be readily extended to other parametric DR methods, making them more accessible for visualizing streaming high-dimensional data.